So wir kommen jetzt zur Keynote. I think it's also for me time to switch to English. Once again, a very warm welcome to you, and I'll give a very short introduction to you personally. Brian is Professor of Aeronautics and Astronautics and Director of the Model-Based Embedded and Robotics System Group at the Computer Science and Artificial Intelligence Laboratory at MIT. And these competencies are, of course, the link why you are here and why we ask you to come and to help us in establishing a picture, a view of the whole robotics scenario and do the right things also. I'm glad that you could come today. I would like to mention that you received your bachelor, master, and PhD, if I'm rightly informed, in computer science and electrical engineering in '89 at MIT. You then worked at Xerox Palo Alto Research Center. I don't know if this still exists as it existed then, but it was an interesting experience, I think, for you, and you did a lot of contributions. He then worked at NASA Ames Research Center and delivered significant contributions to many projects there. For instance, you have been member of the Deep Space One probe flight team, and you are now still member of the Advisory Council for NASA Jet Propulsion Laboratory at Caltech. He is very active in scientific publications. You could make an, I think, endless list on that. And you're also very active in several editorial boards. And you have received a very broad selection of honors and awards for your research work. And we are very happy that you are here. And I'm sure everybody is very much looking to your talk. Now, the floor is yours.
Okay, good. Okay, excellent. Well, thank you very much. I'm very honored to be here. So the talk that I'm going to give you today, by the way, will this timer start at some point? Just want to make sure. So the talk that I'll be giving here today is focused on the notion of can we develop robotic systems in the very broad sense of robotic system where we can interact with them like another human, that specifically that we can communicate to them at a cognitive level in terms of the goals that we want to achieve and the tasks we'll perform. Now, this links to the kind of the two thrusts within Joanneum's robotics effort, right? Both in terms of human collaboration and in terms of safety, but at the level of how do we link goals to actions that we do collaboratively with humans, and then how do we do that safely? Now, in my own research group, about 50% of the group is focused on how do we go from goals to acting kind of robustly in the world. About half of the group is on human-robot interaction in terms of goals. And then the last 50% of it is focused on how do we achieve a set of goals within acceptable levels of risk, that is safely with either respect to humans that you're interacting with and the safety to the robot as well. So we do a lot of work in deep sea or deep space exploration where safety is a big issue as well. Now, I do know math, right? So the way that 50%, 50%, 50% combine together is that there's a very strong synergy between the notions of human interactions, reasoning from goals, and then safety. So we look at the combination of those three ideas together. Now, for the purpose of today's talk, I'll have time to be able to probably tell you about one of those, which is human-robot interaction, right? In terms of a set of goals, I probably won't have time to talk about how to do planning, within safe or risk bounds. But if I have a few moments to do that, then I'll talk about that at the end. Otherwise, I'll be glad to talk to people about that later. But the issue of being able to act safely by having the human user specify what level of risk they're willing to accept, having a system reasoning about the uncertainty of the world to decide how to act is a very, very important theme, right, to actually deploying these systems in the real world. Okay, so my focus, as I said earlier, is to go from the set of high-level goals, right, that a human can communicate down to a system that can act robustly. My notion of a robot, right, is quite broad. So the examples that I'll draw from in this talk will include personal air vehicles, right, which is a little bit of a far-out concept, but I'll explain that in a moment. Human-robot coordination for manufacturing, exploration, and my heritage from NASA was to build I led a group which built an autonomous deep space probe that was commanded in terms of goals. We deployed that mission, and we learned a lot about how to develop rich robust goal-directed systems. That's kind of driven our research. Now we're focusing on the analog, which is deep sea exploration. And then after this visit, then we'll be deploying some of these technologies in the Timor Sea over the next couple of weeks. And then finally, a very different kind of robot, more of an immobile robot, right, are things like sustainable homes. And you can carry these technologies, right, into issues of sustainability, both in terms of you want systems which are robust with respect to the uncertainty of renewables, but are still achieving the tasks that humans want to have. So the link between tasks and uncertainty are very important. Okay, now the common theme amongst these systems is if you look at, for example, just autonomous vehicles, right, but robots would be similar, and you look at how you command them today, then usually you give them a set of low-level commands, right? If you're not remotely piloting a vehicle, then you're giving a set of waypoints that you're having the vehicle go through. If it's a deep space mission, it's a sequence of low-level commands. Underwater vehicles, it's the same. So the level of commanding of these systems are very low level. If you talk about to the Spirit and Opportunity or Curiosity operators at NASA, who we work with, or people who are doing deep sea exploration, then the scientists say that they're spending all their time trying to figure out the low-level commands and making them safe, and they don't have the time to think about the science. Now, when you have a $1 trillion rover, even if it lasts for 10 years, if you're spending all your time doing the low level and your science return is very low, then you're not getting very good value for the system, or you can end up losing the system. For a deep sea exploration mission, it's about $100,000 per day to operate those missions. So again, if you want to be able to get high value, you want the scientists to be thinking about science, not about the lowest level of the system. So the approach that we take is that we want to be able to interact with the system at a more cognitive level, ultimately as if the scientist was talking to a human engineer who was operating the system, right, and that the system can adapt based on those goals. And that makes it easier to command a system, but it also gives the system more flexibility to adapt to unusual situations because it can focus on how to achieve the goals as opposed to the set of low-level commands that was given to it. So you have more adaptivity. So in this case, if we talk about an aerial mission, and we take, for example, the problem of putting out a fire, then you like to be able to say to the system, okay, here's a map, right? Here's where the fires are, here's where you can refuel, here's where you can get water, for example, to drop on the fire. Put out these 2 fires and come back and complete that mission within a period of time, such as an hour, and then have the system robustly do that. So let me give you a simple example. This is about a 10-year-old movie, not very fancy graphics, but it'll communicate the idea. So we say to the system, right, we want the fires to be out in 2 locations, right here and here. There's some water, there's some fueling stations, there's the base station, there's places that we want to avoid, and then we have the system execute that mission, right, given those goals. So here's just an example execution. And there's a couple things that are important about this, right? So we have to fly or navigate the vehicle, right? So that's a traditional navigation problem. You need to give the continuous dynamics for the vehicle and plan a trajectory. So what the system is doing is it's planning a trajectory over a shorter horizon, and it's doing a variant of model predictive control to do this. But at the higher level, it needed to do an activity planning. So in order to put out the fire, it needed to know that it needed to go pick up water, right? It needed to go to the fire. It was then running out of fuel, so it needed to go get the fuel, right? It needed to go get some more water, put out the next fire, and then return to the base. So at this level, it's planning a sequence of activities, right? It's satisfying timing constraints and satisfying resource constraints. So that's kind of a real-world AI activity planning problem that the research community has been working hard to solve, but it's still, the field is getting closer, but it's still a challenging problem. Here we need to have that kind of activity planning with time and resources coupled very tightly with the planning in terms of the trajectory optimization, which robotics is more historically looked at, and dealing with the coupling between the two, for example, in terms of timing constraints. So that's a rich hybrid planning problem that kind of bridges between classical robotics, right, and artificial intelligence, and those are key to being able to perform these kinds of missions. Uncertainty is also very important. So the system is planning dynamically to deal with wind disturbance, but there's uncertainty, for example, in the map. And so the system needs to be able to reason, for example, about the risk of getting into the no-fly zone, the risk of running out of fuel along the way, and managing that risk. So it's a very complex planning problem. But we do have technologies which are starting to get pretty good at solving that problem. Okay, so the question that I'm saying is if we can effectively develop those systems which can do this rich form of planning at the activity level and the motion level, right, and can do it robustly, then what's the human interaction problem? So how do we have humans interact with these kinds of systems which are very capable in terms of planning? Right? So they can respond to you, but those systems don't know things that the human knows, so we do want to make sure that the human can use their model of the world, their goals, to effectively communicate to these systems and have these systems communicate back to the human enough about how it performs the tasks to help the human as the decision maker. So together they work very effectively, right? But we want to be able to support that. So I'm going to support that in a couple ways. The first question will be, if I was going to program these robotic systems, because we program them today, then what kind of programming language would I use and how do I program these systems? So I'll first give you an example of programming these systems, and I'm going to show it to you in a language which looks like Java, just to kind of, it's a little bit of a wolf in sheep's clothing, because we're kind of familiar with programming with Java, but we'll change it a little bit so it goes into goals. I'll give you an example of that. I'll then shift into how do we have actually a human dialogue with the autonomous system, and then if I have time, I'll talk about how these systems work together side by side. So the three kind of thrusts within my group is how do we develop programming languages, right, which look like traditional programming languages engineers are familiar with, but elevate them to the level of goals. And a goal is a state. So what we do is we elevate it to specifying desired states as opposed to just actions. The second is a language executive which can execute those programs robustly. And I kind of given you an example movie of what those executives will do. And then the last part is how do we now build upon these kinds of capabilities to have a fluid interaction between humans and robots. And I'll do that at the level of setting up the problem when the problem becomes too difficult, and I'll also give you hopefully some examples of kind of human interaction with the robot when they're performing a shared task. Okay, a large set of people have contributed to this over the last 15 plus years, 15 years at MIT and another about eight at NASA and at Xerox PARC before. And this work wouldn't be possible without this large set of collaborators, a huge number of students, but also a very large set of collaborations with industry, with deep sea exploration institutions, with Boeing as a corporation and the likes. So I'm going to start with an example of exploration vehicles, right? Air and underwater, to kind of go back to the firefighting example. And I'll use this the notion of, give you an example of programming in terms of goals. Okay, so here's the firefighting scenario again. So we decided to be able to make these, to see whether or not these tools were simple enough to use and that they were usable. We taught a course in January for freshmen who had never programmed before, but we introduced to them the notion of first programming an autonomous system mission, right, in a traditional process in terms of a set of waypoints, and then how to program them in terms of goals. And the objective was to be able to teach people who had no prior background, right, what's this notion of goal-directed planning, and then be able to use these systems. And we gave them a set of challenges, and they would program in simulation. So this is an example of the simulation environment, and then they would program a set of quadcopters, and we just used the cheapest, most commercially available quadcopter, which is the AR drone, mainly as an outreach activity to test the simplicity. So here's an example of a program. It looks like Java, right? So you have objects and methods. Objects have a set of slots, right? So here we have the unmanned aerial vehicle, 2 lakes, 2 fires to put out. And the program is very simple. The program simply says, in sequence, put out the first fire, put out the second fire, and then at the end, the UAV should be back at the base, and it should have landed. Okay, and we can add in timing constraints, we can make it more rich. But that's a very simple program, and it's an instantiation of the goals that I gave you before. We also have to tell the system, right, what's the behavior of these objects, and the main thing we want to do is to specify the states, which is, for example, an air vehicle, right, has a location, which is some places in a roadmap. It begins at the base, and it also has the state of whether or not it's flying or not, and whether or not it's loaded or not. And we can give the states of all the other variables as well. So an object is really just specifying states of the world, methods are changing the state, and goals are specifying what state you'd like the system to be in. Now, to be able to specify what actions the interpreter or the compiler of the program can use, then we give a set of primitive commands, right, that we can give to the air vehicle. We can say, for example, we can land, right? We can load water, we can drop water from high elevations or low elevations. And then for each of these actions, we say what conditions need to be true at the beginning and what conditions need to be true at the end. So before flying, you're flying, and after landing, then you're no longer flying. Okay? So these are really a description of what behaviors those actions can perform. our original program said what our goals are, and then the job of the executive for the program, right, is to piece together those actions to achieve the goals. And in fact, that's what it's doing. We'll also give it a roadmap, we'll give it the dynamics of the vehicle, and then it goes off and flies. So here's an example of a simulation, right, that the students did, in January using this environment. It's just a system called Gazebo, right? So they develop their program, right, then they run it in simulation. So this is just a very sped up example of the scenario you gave before. And here, just the idea is it's at a point where you could program in a fairly simple manner these kinds of systems, right? So we're starting to get close. Now, once they've done it, then what we would simply do is to have them tell the IP address, right, of a set of drones, and then they could execute the drones doing those missions as well, right? And so within a week or so, the students were fairly effective at doing this kind of thing. So that's mainly just communicate the notion that we can actually command these systems fairly simply in terms of goals, and they have a fairly complicated behavior, but ultimately you want to hide that complication and make it simple and more abstract. Kind of lesson from Xerox PARC, which kind of leads to kind of Macintosh, Windows systems, iPhones, and the likes, was take technology and make it very simple to use, and then hide the complexity inside and make it predictable. Okay, so that kind of pushes on the pedagogical side, and now what we would like to be able to do is to make it so a kid can, a middle schooler or a high schooler can download this system on the web, buy, hopefully for Christmas or something like that, be given an AR drone, and then start learning these kinds of concepts and programming them, right? Or in high school teams, they could do this. Okay, so that's kind of one end, right? But we're not necessarily kind of focused on education at this conference today. We would like to impact more of a commercial world. So the next thing we're doing is we're taking this and trying to say, how can we take these kinds of systems and deploy them within the real world in very challenging situations? So one challenge is information gathering, right? So the firefighting example was one example of information gathering. Crop monitoring is another. Different kinds of surveillance, right, are other examples as well. So if we take the capability that I was talking about before and you deploy it in information gathering tasks, right, then what's involved? So one example that we worked on was the problem of how do you find a convoy, right, which has been lost, for example, in Afghanistan. How do you try to find out where that is? Or agricultural examples and underwater examples are actually very similar. So when people are performing those missions, then part of the expertise of an operator is that they have a rich set of different strategies and patterns for performing search. So we need to be able to extend our language of the kind of actions these systems can perform so that it includes different things like the notion of following a road, doing a lawnmower pattern, doing a spiral pattern, and the likes. So we augment our planners that they can speak in terms of those vocabularies. They know what effect of the elevation is in terms of information gain, and the likes, and that they can adapt those different parameters. So we provide a library of those to the system beforehand, right? And then the mission operator will say, here's some goal. So for an example of the goal for the convoy is that the goal is that we haven't heard back from the set of vehicles. Please go off and try to find them. It needs to hypothesize where the vehicle was taken, who took the vehicle, what are their goals, and where they're going. So the system needs to be able to take a set of goals, right, about what human behavior was to try to understand what might have happened in the world, and then the system needs to use that information to say what are the most likely places for the vehicle to go, and then it needs to do the kind of planning I showed you before to piece together those actions, but performing those actions with respect to information gain. Okay, and that's what the system is doing here. Now, I won't show you a movie, but it's kind of similar to the firefighting, but it then augments the system's ability to be able to gather information, right? So information gain is key, and the ability to be able to deal with kind of richer notions of the behavior that they're trying to characterize and a richer notion of the actions to perform are key to having this work. Now, I mentioned that after I leave here, then I'm going to be getting on board a ship, right, for 2.5 weeks, right, in Broome, which is probably the most difficult place to get to in the English-speaking world. And then this ship called the Falcor is going to go off for 2.5 weeks to the Timor Sea. And it's a 2.5-week effort to take a range of autonomous underwater vehicles, both ocean gliders, right, and a set of powered, right, autonomous underwater vehicles, and have them work in cooperation. So this isn't a science mission. Usually these things are science missions, just as in NASA we mainly focus on science. This is actually a technology validation mission to say, let's validate the technology and have science be second. Normally, science trumps technology, and you don't get to do anything risky. So there's a large team of people who are expert in operating these kinds of vehicles in the field. We're joining in as a group with expertise in mission planning to do the planning for single vehicles and then ultimately move towards multiple vehicles, but at the same time to learn a lot about what the science objectives are. And this is where we're going. So here's Broome, here's Darwin, Perth is down here, and Scott's Reef is where we're going, which is there. And so our job is to map out that area, right, kind of dynamically. Now, in these kinds of missions, right, unlike the aerial vehicle missions, then loss of the mission is very important, right? Colliding to the seafloor, going below an overhang, and then if you try to go to the surface, right, because of an emergency, then you get caught in the overhang, and you have to send a remotely operated vehicle to get it. So a lot of what we're doing in this case is to be balancing planning within acceptable levels of risk, right, together with how do you achieve your information goals. Okay, so that's it in terms of systems that you command, in terms of programs, in terms of goals, and then have them act on your behalf while dealing with the dynamics of the environment, right, and dealing with uncertainty. What I want to do then during the remainder of the talk, right, is to talk about the human interaction with the system. Right, so we've gotten used to, for example, Siri's as a device, right, as a simple example of a system where we can interact with it at a cognitive level. Google Maps would be an example of that, where it can perform actions on your behalf. So that's a simple example of a goal-directed system, which is doing some planning, but there's a much richer notion of planning. So the problem that Boeing gave us, right, as kind of a fanciful problem was, suppose we have a personal air vehicle, right, which is a car that can drive on the surface, but it can also fly. Right? And the question is, if we want to have a large market for this, then we don't want people to be certified pilots. So we like to interact with the vehicle as if we were interacting with a trusted taxi driver. And that trusted taxi driver should be able to fly the vehicle safely. It should know about how to not get into too risky situations, such as flying into complex storms, right? It should know how to avoid those storms. It should know to get you to your destination on time. For example, if you have a connecting flight. It should also be able to kind of give you good advice. What restaurant should you go along the way? How long will it take? How good is it? And then go beyond. So that's the kind of capability that we've been developing. And so let me just give you a little example of the prototype that we had demonstrated. Do we have sound?
Any more preferences?
So let me just restart it.
I want to go to the Boeing company.
Any more preferences?
I want to be there in 3 minutes.
Anything else?
I want to stop at Leisureland.
Any other requirements?
No.
We cannot get there in 3 minutes, but we can get there in 6 minutes.
That's fine.
Okay. I have a valid plan. There is a change in the weather condition. I will replan the path. The current destination is unavailable. Diverting to the preferred alternate landing site, Harvey Field.
Okay, so if you look at the different capabilities we have here, right, then it is maintaining a collaborative dialogue, right, both in terms of you can specify your goals, but when it can't achieve those goals, then it's trying to explain to you why it can't achieve those goals, presenting alternative options and try to come to some consensus. It does always have a backup plan, right, so it does know different contingencies, alternative landing sites, right, and it has the ability to be able to kind of very dynamically switch between those backup plans or to reason about constantly which of those backup plans are applicable. It knows about managing risk-taking. That was less clear here, but what it's trying to do is it's piloting the vehicle at the trajectory optimization level. It's trying to assess what the risk is, for example, of going into the weather system or arriving too late, and it's balancing that risk against what the user would have told you in terms of what was acceptable. And then finally, it's constantly monitoring its environment. It's saying, are there goals that will be defeated? Will I fail sometime downstream? And then how do I adapt accordingly? Okay, so in order to do this, there's a number of different levels of reasoning, right? We just have selected these names to help people to kind of understand the level of reasoning. So at the lowest level, it's navigating the vehicle, which is trajectory optimization, but it's doing this within a bounded risk using a model of uncertainty. We are doing the planning at the activity level, which is roadmap planning, like we get in Google Maps, but it's balancing time against motion, right? So it's tightly coupling scheduling against motion. And then that gives a set of goals, and then the thing that's doing the navigation has to navigate the vehicle. So it's just trajectory optimization, but it needs to do that with respect to a set of goals and states. So the coupling between these two levels are very important. Together, these two are trying to achieve the user's goals, right? If those goals are not achievable, then we need to diagnose why the plan is not achievable. We need to present other options to the user, and that's performed by a system which is doing reasoning and diagnosis to collaborate to come up with a set of goals. And that's kind of the last level. And they're all kind of working in concert. So let me just kind of take the upper capability, unserer, which is our communication system, right? So it's really doing a form of diagnosis, but it's diagnosing why the user's goals are not achievable. So when we receive the dialogue, which is just speech and natural language parsing, then when we got a sentence like, I want to go to Boeing, then that was simply saying that there's some goal, which is to arrive at Boeing, and here's the time bound which we want to achieve. And each of the sentences are just giving us different goals and time constraints. It looks like a plan, but it's a very high-level plan, which is saying what goal states we want to achieve and what are their temporal constraints. And then the system tries to elaborate that. So it tries to come up with an activity and motion plan, and it imposes additional constraints. So the planning system will say it takes 10 to 15 minutes to arrive at Tacoma, right? 10 to 15 minutes to arrive at Boeing. And then what we notice is that we can't satisfy all these timing constraints. It would take at least 30 minutes before we can leave Tacoma, but we have to do it within 25. So the system diagnoses that as a failure and then presents alternative options to the system, such as leave as early as 15 minutes to try to resolve these kinds of inconsistencies. And if I continue, then the process becomes more and more rich, where there's many different conflicts. We have to be able to resolve them all. Okay, so let me just show you how the kind of behavior you can get if you kind of enrich the kinds of options that the system can have. So in this case, we'll also have the system be able to try to relax your destinations as well. In this case, an intermediate stop at a restaurant.
The PTS is ready. I will stop at a gas station first, then take you to a 4-star restaurant before going home. How much time do you have for this trip?
Complete the trip in 9 minutes.
I cannot complete the trip on time. Here is an alternative. Go to Pike Place Market for dinner and relax the trip duration from 9 minutes to 11 minutes. Is that okay?
No.
I can take you to a 2-star restaurant rather than a 4-star restaurant and only relax the duration from 9 minutes to 10 minutes. Is that okay?
No.
I can take you to Burger King rather than 2-star restaurant and complete the trip on time. Is that okay?
That's fine.
Okay, shall we start?
Yes.
Okay, sit back, relax, and enjoy this trip.
Okay, so user modeling is important here, right? So the system now kind of goes over the web, looks at a set of recommendations, develops some notion of how close what the user wanted, such as 4-star Chinese restaurant, to some other option. You can tell that different people's preferences are different. So as you're having this dialogue, it's trying to adapt its model of the generic person to the user model themselves. So hopefully for you, ultimately the recommendations it would provide would be different than my graduate students, which are Burger King or something to the like. Now, of course, Joanneum is more focused on robot manufacturing, so during my last just couple minutes, I'll cross over to robotic manufacturing and the likes. But many of these technologies apply either in terms of how human and robot would interact together at a partnership level or in terms of strategically managing the factory as a whole. I'll focus on my remaining time in terms of the human interaction and working side by the robot, but carrying this over to managing the overall factory floor is a fairly direct translation, because at the overall level, you're dealing with time, resources, and the likes. Okay, so the example that Boeing has been having us working on is how do we assemble a wing, right, where we have humans and robots working together. So we have a set of robots which are picking up, for example, assembling a wing. So you have a strut that you want to pick up. The human will be kind of stepping in to do things like like inspection. You do have to do things like cooperative lifting, right, that you need to move continuously. The robot arms need to move and be in position at the same time before they can lift together. So a lot of planning at the activity level and the motion level, right, together with the coupling with the human, which is the new mix into the factor. So in order to be able to do a fluid collaboration, there's a number of things that you need to address, right? So you want to be having the human and the robot working together and to constantly adapt to each other. We don't want them to do a lot of talking, but they do want to understand what the shared plan is when they do that adaptation. We want them to be able to kind of replan very quickly, but in novel ways to respond to the situation. I'll try to give you examples of that. It's also the case that you want to be able to understand what the human is likely to do and anticipate the human to respond. And I won't have time to give you examples of that. And then finally, you'd like the system to be able to learn by observing the human new ways of performing activities by the robot. And again, I won't have time to touch that as well. So let me give you just 2 examples where the system is going to be adapting to the human. So in this case, I'll give you 2 robots, right? And these 2 robot arms, right? One of them, in these cases, are kind of proxies for the human, right? But other examples, we have the human involved. Here we just have a set of shared tasks, right? Which is we have a deadline that we want to meet. We have 4 bins that we want to take a ball out of, and either robot can take a ball out of it. And then we want to take a ball from here to here and a ball from here to here. And those are these 2 tasks here. Now, these 2 tasks are cooperative tasks, right, that we need to work together to perform them. And these are side tasks that either robot can perform, right? So they'll try to perform those when there's some extra time. So we tell the system, here's the overall plan, right? So they have the shared plan, and in this example, we'll have the model that the robot, if the robot needs to do something to help succeed, then the robot will do that. But if the human needs to do something to succeed, then the robot can assume that the human will step in. So that'll just be a simple model. And then what's interesting in this case is the only communication you need to have is that when a robot decides to do something, it says, I'm starting this task, and when they finish it, they've finished this task or activity. And with that level of communication, you can get a very fluid interaction. For me, the metaphor was that when I had little kids, my wife and I, when we get the kids to school, seemed to adapt to each other without much communication. You know, if she was serving them breakfast and she hadn't gotten her clothes on, then I would run upstairs and go take a shower and then take the kids to school. And we really didn't need to talk about that. So so here's just an example. So in this case, they're performing the task, right? The left robot picked up the ball to swap it. The right robot, without being told, said, okay, well, I better get over there and pick up the ball. And the reason why they did it is that if it didn't and it did a side task, they would have run out of time. Now, the second robot arm, we're going to inject the failure by grabbing the arm, right? And so the other robot arm doesn't sit there and wait. It just kind of goes off and does the side task of picking up and dropping off the other balls. Because, again, it wouldn't have succeeded. And there's a couple of different kind of models that we've explored in my group with Patrick Conrad, Julie Shaw, Phil Kim, and others. Okay, another notion, just I'll probably try to end with this one, is in the previous case, the decisions that the robot were making was just adjusting the time that it would do an activity and which activity when multiple robots could perform it. So this is really just doing the classic notion job shop scheduling, which is resource assignment plus scheduling, but you get a very interesting emergent behavior if that can respond very quickly. What the system wasn't doing is it wasn't coming up with a new plan of action to achieve its goals, like we did in the firefighting. So the last example I'll give you will be an example of a system where it's able to kind of plan a set of activities to achieve a set of goals. And it will be constantly monitoring when things could fail or not. A human counterpart is going to be helping or hindering along the way, and then the robot's constantly adapting. And the fact that the system can monitor kind of failure very quickly and kind of replan very quickly gives you an interesting emergent behavior. So the setup is we're going to ask the robot to stack 3 blocks in this order, which is a classic problem AI has been working on for about 40-some to 50 years now, right? There's a set of cameras here. From those cameras, it recognizes the objects with a little bit of help from these fiducios. And then here's the view that the robot has of the world, right? Which is a little bit uncertain, but it's fairly effective. It is then constantly looking at this world, coming up with a plan to achieve these goals. And if it detects that those goals are defeated, then it's going to adapt. If it can't achieve its goals, then it will ask the human for help.
Hi. In this video, we're going to demonstrate fluid human-robot interaction in situations where humans can be both helpful to the task execution or hinder task execution by adding disturbances. Make Helen.
Okay, I start presenting.
So the system fairly quickly planned the actions and
The robot can't reach the pink block right now, so it will notice that and ask for help.
I can't reach my destination.
Okay, so since I'm a nice human, what I'm going to do is I'm going to help the robot by moving the pink block closer to the robot. So I'm going to add a disturbance. So once the robot picks up the block, I'm going to add the green block on top of the red block.
So whenever the robot says, oops, it has detected that its plan has been defeated, and then it kind of quietly goes off and generates a new plan to adapt. Okay, so it'll keep doing this.
I'm trying to put the pink block on top of the blue block, so just move the blue block a little bit closer to the robot, and then it will be able to complete its task. So once again, I help the robot.
So if we continue that, right, then the human ends up kind of doing some of the parts of the task. The system kind of quickly says, okay, well, gee, now that that's done, I'll finish the rest of the plan. But what's kind of nice is the kind of fluid interaction you'll have. To be able to do these kinds of planning in the real world, right, then you have to develop planners which can deal with time, concurrency, and resources. And so much more capable planners have been developed kind of within my group to deal with that. Okay, so with that, what I'll do is I'll just close, right? We've also extended these ideas, right, to, for example, energy systems, a very broad set of systems. And the idea is that these technologies can carry over in a very wide set of domains. And the features of them are that they're goal-directed, that they're robust to failure, that they do try to optimize, either in terms of information gain or efficiency, that they know about risk, they know how to collaborate, and they can use these technologies to seek information as well. At the core of that is then a set of languages to program at the cognitive level, a set of executives, right, which can take those goals to actions, and then finally a set of interfaces which leverage upon those technologies to support a human fluid interaction. Okay, so with that, I'll end.